especially Dr. Duncan and his staff, Gloria Smith, and others who arranged this and set up all the support. What I'm going to talk about today is 20 years of history and research that we have been performing in this area. We currently call it low-energy nuclear reactions. That may not be any more accurate than the term cold fusion, but it's one that the field has kind of adopted. We're going to do a little bit of a tag team. In addition to myself, Dr. Pam Mosier-Boss is going to be doing part of the presentation, and also Larry Forsley is going to also be involved. And we are including work that has been done by Melvin Miles and Mitchell Schwartz in the presentation. Right off the top, I'd like to offer a little bit about how do you survive 20 years in this controversial field. And Dr. Duncan talked about the importance of following the scientific process, and that certainly has served us well. Carefully design experiments and conduct those experiments, repeat and validate the results, submit those results to peer review, respond to the referee's comments, and publish, and then based on that design new experiments and continue to advance the progress. By doing this, we've essentially been hiding in plain sight. We have 23 peer-reviewed papers and 2 articles in New Scientist, plus the National Public Radio did a feature on our work, numerous web-based articles, and most recently the Discovery Channel Brink did an article on us, and throughout all of this, the reception that we have received certainly was much better than what Pons and Fleischmann received when they made their announcement. And in fact, there at the bottom you see some of the most recent remarks. Bob Park, who wrote Voodoo Science and has been very skeptical of cold fusion, is now admitting that this is science. Johann Frenge from MIT, who's in the hot fusion group there, after looking at our results that were presented at the ACS meeting in March, in a quote in a New Scientist article, said the data and their analysis seems to suggest that energetic neutrons are being produced. And your very own Rob Duncan said this is not pariah science anymore. So anyhow, a lot of things have changed in the last 20 years. Going back 20 years ago, here was the situation in March of '89. Pons and Fleischmann made their announcement. The physics community said, hey, their experiments aren't repeatable, there aren't any refereed papers, the experiments haven't been replicated, and if it's nuclear, where are the neutrons? These are probably some of the politer comments made. For those of you who were around then, comments, if this is really nuclear, we don't need a calorimeter to determine that it's nuclear. If it's really nuclear, where are the dead graduate students? There were several comments like that. But in spite of all that, thousands of scientists worldwide attempted to replicate the results. And after all, Pons and Fleischmann were both very respected scientists. I think the Time magazine kind of got that right here when they said it stirred excitement and outrage in the scientific community. And I probably don't need to tell you this, you probably know it, but just to remind you a little bit why some of the controversy between the chemistry and the physics community, and it's shown here. Chemical reactions typically liberate less than 5 electron volts per atom. Nuclear reactions are millions of times more energy per atom than chemicals. So when you had chemists standing up saying we're seeing 30% excess energy, it just, how do you get there? It was just too far of a bridge to cross to get up to nuclear reactions, particularly with the other problems that they have. A lot of people went into the labs to try and do these experiments, as I indicated. And the Fleischmann-Pons approach is shown here on the left. A lot of things, we kind of think we understand why some of them failed. For one, was they may not have had the palladium rod completely submerged, and what would happen is the deuterium would load in the solution and then diffuse up and diffuse out into the atmosphere. So you never did achieve the loading in the palladium. The history of the palladium was unknown. In a lot of cases, a lot of universities, you found a chunk of palladium, you decided, well, let's use this without any knowledge of what was the real condition of that palladium. And the other thing is lack of recognition that there was an incubation time of several days to several weeks before the reaction would display itself, and most people didn't understand that. At Speyer Systems Center, we devised another technique to do the experiment. Dr. Stan Spock, who was an electrochemist, he and Dr. Boss were working in developing high energy density batteries for torpedo propulsion at the time. And they said, you know, rather than try and load a palladium rod, let's start with palladium chloride and a lithium chloride solution in deuterated water. When we apply a current, what will happen is the palladium will plate out on the cathode, and as it turns out, that's also where the deuterium will evolve. So what we were doing is we were loading the deuterium into the palladium as it was being built up on the cathode, and in the picture there in the upper right, you see the structure of the electrode after we took a look at it with a scanning electron microscope. You see a very cauliflower type approach, a lot of surface area. You know, they say if you have a choice of being good or being lucky, choose be lucky. I think in this case we were both good and lucky. Certainly it was a good idea to do this. We were lucky in that now we understand. I think we have a great more understanding that surface area is very important, and clearly this technique produced a high surface area. We have an understanding that defects in the lattice may be very important, and in this process we were actually building the defects in at the time. These were things we didn't necessarily appreciate at the time we devised the scheme. The main reason we did this was because we didn't want to wait 2 weeks, and so the advantages of co-deposition, short loading times with measurable effects, and you see 3 of the publications in general in the presentation. Whenever you see a reference like that, it represents one of the 23 papers that we've published. These experiments were extremely high repeatability. It maximizes experimental controls, and you'll see how we take advantage of that several times over the 20 years, and extremely high surface area and defects built into the lattice, as I've already mentioned. Here's an example that shows how fast we saw the reaction. You see there in the chart in the middle 2 experiments. One and in both cases the cathode was hotter than the solution. We had thermocouples, one affixed to the back of the cathode, one in the solution, and in a matter of less than an hour we were able to notice that the cathode was significantly hotter than the solution, or measurably hotter than the solution. That shouldn't be. Yeah, if it's joule heating, then the solution should have been hotter, and certainly the solution was higher resistance than the cathode. So, you know, this was a surprise. This is something that we shouldn't have seen. Also, Pons and Fleischmann talked about a phenomena called heat after death, and we observed that also, where when we turned things off, you'd get a burst of energy, and so something was happening here that we didn't understand. We didn't do a lot of work with calorimetry, and for a variety of reasons, but one of our co-workers at also a Navy lab, Dr. Mel Miles, who was at China Lake, did some experiments using co-deposition and calorimetry, and again, so not only was he able to do this and achieve these results repeatedly, they also occurred very quickly, and he showed that the co-deposited cathodes produced excess heat equivalent to what was being produced by the bulk palladium cathodes. And in fact, he also talked about the positive feedback, another phenomena that Pons and Fleischmann had talked about. And you see on the left the expected behavior when the rate of excess enthalpy remains constant, and then you see on the right the positive feedback effect. Dr. Duncan mentioned a couple of times that you know, every time we looked for heat, we saw excess heat, and that's correct. When we looked for heat, we realized we really didn't understand what was causing it, and so we have spent the bulk of our time looking for designing experiments and looking for results that would help us understand the underlying physics that are occurring. And one of the things that we did was we took an IR camera, we cut a hole in our cell, and by the way, here I have a typical cell that we use. It's costs less than $1 at a hobby store. This one already has the hole cut in it, and you put a Mylar window over that and then view it through an IR camera. And when you do that, you see the kinds of display here in the upper left. We were able to observe how the electrode heated up during this process, and so it wasn't just a gradual heating up of the whole electrode. There were spots that were occurring. Dave Nagel, retired from the Naval Research Lab and now at George Washington University, who is also here today and I think going to be one of the speakers, did some calculations based on the size of the pixel size of these spots as they were, the flashes, looking at the energy being conducted away, and determined the bottom line was that the hot spots must be due to nuclear energy release. We took advantage of the co-deposition, and this is one of the examples in experimental flexibility. We showed the IR data to Lowell Wood from Lawrence Livermore Lab, and he said, hey, you guys in the Navy, why don't you put a transducer in your cell, because these should be leaving signatures. You should be hearing these. These appear to be mini explosives. Well, we're the Navy. We did one better. We took a piezoelectric material, co-deposited right onto the face of the piezoelectric material, which is shown here in the upper left. By doing that, we were able to get a direct input of these events when they occurred, and the two plots along the bottom show the kinds of results we would get. You get a very sharp pressure spike down, and then followed by a temperature spike that would then gradually decay, and the pressure spike would travel much faster than the temperature, and so as a result, we did some calculations, and based on this, we felt that this is an indication that in fact the reaction is occurring very near the surface of the electrode rather than in the bulk of the electrode. Other experiments that we did looking for nuclear signatures, photographic film. You see on the upper left, after we had conducted an experiment, and this happened to be with one of the piezoelectric material transducers, we dried it, put a thin piece of Mylar or something between it and film, did this in the dark room, put it inside a dark envelope and left it for a few days, then took the film out and developed it. And when we did that, you can see that the film was fogged. We have other detectors, that gamma ray detector and X-ray detectors, so we have seen other evidence of nuclear reactions. Low intensity radiation, in this experiment you see on the right an X-ray and a gamma ray signature. These were conducted at the same time. They were on separate electrical circuits, and you can see that in fact the data seems to be consistent. They were both tracking, so that again this offers more positive indication that nuclear events are occurring. Tritium production was another thing we looked at, and published this in Fusion Technology. Did a very careful tritium experiment. One of the problems, or one of the challenges in publishing papers that purported to produce tritium, is that there's some tritium in deuterated water, and so how did you know that you in fact produced additional tritium? And it's even a harder case to make if you have to replace, if it takes a long time to do the experiment and you have to replace and add more deuterated water, or you're providing a natural enrichment of the tritium. The fact that our experiments occurred over a much shorter period of time made it easier for us to make the argument that no, that was not the case. And in fact, when we did these experiments, we had 3 out of 5 experiments we did produced tritium production rate that, if averaged over a 24-hour period, was between 3,000 and 7,000 atoms per second. 2 experiments showed a complete mass balance. Did not show any additional tritium. As you can see here, although we say it's 3,000 to 7,000 atoms per second over a 24-hour period, we really don't, the indication is that the tritium production occurred in bursts rather than in a uniform period of time over that time. One of the other things that we started looking at is the impact of an electric and magnetic field on the results. And in the cell on the left, you see we have two permanent magnets there, and just, you know, they're strong enough that they hold themselves to the cell. In the cell on the right, we just taped, literally with Scotch tape, a couple of copper foil strips that were attached to a regulated high voltage source, something that we bought at a used electronics store for $7, I think, because this is a low budget operation. And when we did that, in the top center, you recall the surface morphology that we saw when we just did the co-deposition in the absence of either an electric or magnetic field. In this case, you see the pictures of the electric field. You see formation of fractals, in some cases long wires, some folded foils, and even craters, which could indicate something, you know, relatively violent or something happened. A lot of energy could have been released there. These microvolcano-like features, you know, that we see on the left when the applied electric field, in fact, also matched sonofusion of thin foils that Roger Stringham has done, and recall from the pictures that Dr. Duncan showed from energetics, the same kinds of things. And so this is consistent with what others were seeing in this field. And note the middle on the left, you know, that looks like something where a high energy release, it melded the metal, it ejected it, and then it quickly recrystallized, because recall, this is all underwater. If in fact you're getting this kind of reaction, then it would suggest that maybe there are other things that would be evidence of nuclear reactions, and one is there transmutation going on? And so if we took a scanning electron microscope with EDAX capability and put the crosshairs on the rims of the ejecta, what we found was significant examples of aluminum and magnesium, you know, metals that were not there when the experiment was started. Here's another case where you can see magnesium, silicon, aluminum, and zinc. When we published this paper, it was in review for, I think, 7 months. Dr. Duncan talked about it's good to get harsh review. I think this one qualifies. It went back and forth several times, trying, you know, with them forcing us to say, convince us that this was not contamination, that this wasn't there to begin with. And ultimately, we did several, you know, blank and control experiments. We went back to them and finally pointed out that even if we had put aluminum in solution at the time the experiment started, it would not have deposited from an aqueous solution onto the cathode. And so at that point, they agreed and allowed it to be published. In a magnetic field, we saw similar things, except a much higher incidence of iron, as you can see here, and you can see how many of these little craters there are on the picture on the left. We weren't the only ones that were seeing transmutation effects. And in fact, Professor George Miley from the University of Illinois compiled a list of groups that were reporting transmutation. And you can see there are groups here in Japan, Italy, Russia, China, the USA, and again, a couple more in Japan. On the right, you see the number of labs, like 11 labs of these 15 reported. They were seeing iron, 8 said copper, you know, 7, 6. And then on the very bottom, you see the materials that we were seeing. So you can see that we were also seeing some of the same results that the other labs were seeing. I think this is a particularly strong evidence because only ourselves and Bacchus at Texas A&M were using co-deposition to do this. In the case of Japan, it was gas loading. In the case of Israel, it was and they're not even on here, I don't think, is the bulk loading. So the fact that all of these experiments are producing these transmutation results is I think stronger evidence than if everyone did the same experiment and got these results, because this way no single error on the part of one or all of the various experimental groups could account for it. At this point, I'm going to turn over to Dr. Boss to talk about some of our high-energy particle work.